Yes, sir. Dear all participants, good morning and hope you are all well and good. I'm Vignesh Rajmuniratanam, Assistant Manager for Technical and Training in IWMA and your host for the day. On behalf of IWMA office bearers, executive members, speakers, and senior manager, I welcome you all for IWMA ninth webinar session on Advanced Integrated Solution to Treat Industrial Effluents. Dear all participants, now I welcome our chairman, Mr. K. Bhaskaran, to give us a welcome address. Mr. K. Bhaskaran has served as an executive member and presently the chairman of IWMA. He is also holding the position of secretary in Kakalur Industrial Estate Manufacturing Association and also A6 district chairman for e-waste management in Lions Club. Our chairman is a CEO of Orti Industries, an electroplating unit located in Ambattur, Kakalur and Padapai. Now I welcome our chairman on behalf of all participants and the speakers. Welcome, sir.
Thanks, Vignesh. Good morning to you all. Morning, today's speaker, Mr. Magesh and Mr. Vijay Bhaskar sir. I welcome you for this our webinar session. And your topic is also excellent. Actually, in fact, some of them they asked me, even they registered me for 225, I think, as of now. But as of now, participant that's come only 97, something like that. So our industries are more welcome about your topic particularly, because you are going to give a very good this thing to us, because we are all handling hazardous waste from the industries, various industries, automobile, textile, name it, any industries who produce hazardous waste, they will become a member to us. So we give them service like trainings and technical support also, and even in fact treating the water also we give them some solution. In fact, one of the company we have given a very good solution with the help of CLRI, and now he is not a member. So that kind of technology we are having. Of course, not IWMA. On behalf of IWMA, we have gone to CLRI. CLRI is given the solution, and that company in worldwide 120 countries they have implemented the system. Previously, this waste all coming to our landfill site. Now it is not coming to us. It is going to co-processing. So environment has been saved, and it has spread to across the world. So that kind of technology we have given it to industry. The company name I can spell it out. Prudenberg company. It is in Madurai. In fact, they are very much happy. Even this seminar also they said we will participate, sir. So that kind of interest is there for the members. So IWMA is doing a lot of works to you. So please join with us for any, this kind of webinars. And we have a site in Gomudi, and one more site is going to come in Bargur. And we also have our partner is having Madurai, nearby Madurai. So that is our landfill site. And apart from this incineration facility, we have in Gumudi only. As of now, it is running. In fact, in the COVID situation, we have helped a lot to the government also, Tamil Nadu government. And so like that, we are having tie-up with the other technical supporters. And in fact, IIT Madras is also supporting us. They are coming and doing the audit, how we are managing the landfill site. That is, our landfill site is scientifically managed and audited by IIT Madras. Once a year or 2 years, we'll also go monthly wise. We are doing audit. Our technical team is there. They will go and check and how we are doing. In fact, industries, if you are interested after the COVID, please do come and visit our landfill site as well as incineration facilities. So that is part major thing we are doing it. And apart from this environment program for the students, so we are creating awareness among the students. So for that, we are tied up with the IIT Madras Chennai. We have to thank IIT Madras Chennai because they are giving platform to perform the students in environment. So totally it is an environment related project only. We give them some project related to environment. Even as example, they want effluent water to be treated. So give me some solution. So they will come and present, like they will not just go to the Google and search and they will come and present. Not like that. It has to be practical. Practical manner. Even some see 6th to 12th students they are presenting. So every year we are conducting and we are appraising them by giving Young Environment Scientist Award at IIT Madras. So that way we are motivating the students. Same way we are running on Coimbatore also. Recently, last year we did in PSG College. Thanks to PSG College. PSG College is supporting us. So, same way in Coimbatore, in Madurai, we are planning to do that. Recently, we tied up with the Madurai Kamaraj University for technical things. And same way we are going to do that there also. So across the Tamil Nadu, we are planning to do. And we want to create environment related awareness to the students. And of course, apart from the students and college level also, we had a big level competition. And say thanks to IIT Madras, Carbon Zero Challenge program we have conducted along with Polaris and US Consulate of Chennai, the IWMA and IIT Madras. Around in South India, 430 colleges participated and they got some prizes, 25 lakhs, 10 lakhs, 30 lakhs. Not only the prize, and they some one major thing, it went to up to Prime Minister level. They got some award also. So and he has started business also, startup business. So that kind of motivation we are giving IWMA. Apart from this, even landfill side we are ending, but nowadays we are not promoting any landfill activities. We want to promote co-processing because in cement industry they take two type of raw material from us. That is hazardous waste can be used as a raw material as well as fuel. So some lime content they can use it for raw material. If it is high calorific value, they can go for a burning. Cement industry they need 1300 degree they have to heat. For that they are taking all the hazardous waste. So scientifically they are burning. So it has been approved by government and government CPCB and Tamil Nadu government is also they given a target to the cement industries. They can use the 25 to 30% of the hazardous waste there as a co-process or raw material. So that also we are promoting. So we don't want to build a mountain that is a landfill. So that way we are working on it. For that, in industry we need your support. So please come with us. We give some samples to us. We have technical teams. We will give it to them. Like water, how today we are going to have a very big session for how water has been treated. So that is possible. Everything is possible, but only thing is time will take. So that is also one option is there. And some small example I'll tell you. See, in one of my estate, in Kakulur Industrial Estate, we have one person. What he is collecting all the waste, rubber gloves waste and all, and he is shading it to sending it to tarpaulin. So if you segregate and give any material that can be reused, reprocessed, so co-processed. So waste, if you keep waste separate, if you keep in separate and it be segregate and give it as, it is possible. Not only as, it is you can give it to anywhere, even for the household thing also. Same thing it can be happen. So like that we can improve a lot of things. So please come out with the problems, and we will also come with you. We can give some fund also for any kind of some small amounts we can give. That is possible. IWMA is supporting. IWMA is ready to support because our committee members, 16 members committee is there. They are all committed. They are all from different industries from all Tamil Nadu. I am also part of it. Once again, I welcome you participants because every week you are giving very good support to us to run this webinar. So we will keep on doing these webinars for next couple of months. For that has been fixed 11 to 12, 12:30, 1 o'clock. It is a regular programs. We have a speakers lineup already. We have in hand. 12 speakers are there. So please support us. And again, I welcome you this today's program. Thank you, sir. Welcome, sir. Over to Vignesh.
Thank you, sir. Thank you for addressing our participants, sir. Dear all, without any further ado, we will start today's webinar on advanced integrated solution to treat the industrial effluents with two honorable speakers from Iron Exchange Limited, India, Mr. Mahesh Kalyanasundaram and Mr. Vijay Bhaskar. Mahesh Kalyanasundaram has been based in Chennai since Jan 2016, work for Iron Exchange India Limited, and pioneer and the leader in water and wastewater treatment technologies in South Asia as a regional head for South India. Prior to this, he was in a Siemens, a German multinational company for nearly 25 years, serving in India, Germany, and for 16 years based out of the United Arab Emirates in various capacities. He is an industrial and process automation expert and was involved extensively in water supply Siemens schemes in United Arab Emirates, as well as water, wastewater treatment, and water reclamation technologies for large municipal and industrial facilities all over Middle East. He holds a bachelor's degree in electrical and electronic engineering from Sastra University, Tamil Nadu. And about speaker number two, Mr. Vijay Bhaskar sir is a divisional manager, corporate marketing, Iron Exchange Limited. More than 19 years of experience in business development with a leading organization like GlaxoSmithKline India Limited, Fine Chemical Business, Milesport Bioscience Corporation, and Iron Exchange India. He has been associated with Iron Exchange Limited since 2004 and is part of the company for several initiatives in marketing and promotional, channel management, client relation management, strategical and business development planning for South region. Also involved in business development in EPC projects and the product marketing in arena of water and wastewater treatment. Now I welcome our both speakers on behalf of all participants, IWMA executive members and senior manager, and I personally welcome you both of you, sir. So kindly take over the session for the day.
Yeah, good morning. Thanks a lot for the introduction.
Welcome, sir.
Thanks a lot for IWMA, Mr. Bhaskaran, for organizing this webinar. The topic, of course, is very relevant for us these days. India has, a lot to catch up with respect to strict implementation of effluent and industrial pollution. I mean, we also saw a lot of news reports recently in the paper regarding the river water quality improving with the slowdown in COVID. So we hope we also will have a speed up on the industrial activities with a similar, pollution control strictly implemented as we get along into the future and create a, post-COVID India for us. So thanks a lot once again, and very warm welcome to all participants to this session. We have roughly about 1 hour's time planned. So we broke it up into two broad areas. Since the diversity of the crowd is very high, we said we'll have the first 15-20 minutes just touching up upon the basics so that everybody is on the same level with respect to understanding what problems we are trying to solve. And then the second session, Vijay Bhaskar will take over where we go into more details about specific products and technologies. So what we will cover now, is a very quick introduction of our company, just 1 or 2 slides. Then we get into the basic design issues, challenges, and then, of course, like I said, into the more detailed applications of technologies. So on the right, you see a picture. This is an effluent treatment plant in India now. So India has come a long way. From looking at dirty tanks to almost a sterile shop floor. Environment where you have a really state-of-the-art technology implemented. For handling effluents and handling a complete recycle of water. So this particular plant is a zero liquid discharge plant set up in Andhra Pradesh. Yeah, and just gives you an idea, how modern ETP looks like. That is what we are all coming towards now. Yeah, we can go on to the next slide. So, like I said, a very brief introduction. I will start from my company. A lot of details about what we will talk today in terms of technologies, products, application notes are there in our website. So you can always log in there and download. It's free for all. It's information available. Yeah. So we are a 50-year-old company. In fact, 55 years old now, and a leading player in the Indian market, also in the Asian market. We do complete projects in a variety of technologies for both water treatment, wastewater treatment, effluents, zero liquid discharge, high purity water, pharmaceutical grade water, the whole water cycle and wastewater cycle we cover. Yeah, we also are into manufacturing not only equipment, but we also manufacture chemicals and special purpose resins, which are used for in the water industry as well as in the pharma industry, variety of applications. So this is a rather unique combination where we make equipment. We also have a very strong chemical engineering team with a very strong R&D backup. With several manufacturing locations all over India, dedicated for specialized technologies. We also operate globally, exporting quite a few of our products to the Middle East, to Europe and UK. In fact, a lot of our products, high purity resins go into the pharma industry also abroad. So that gives you a rough idea of our capabilities in terms of FDA approved facilities for production and traceability when equipment or material is used in the pharma industry. Yeah, and of course, a large service setup all over the country assures our customers that are taken care of in terms of issues, applications, so on and so forth. And of course, with respect to quality, we can't do export and also survive in the Indian market for such a long time without having a very, very high quality standard, and that is what our certifications talk about. Can you go to the next slide, Vijay? So this gives you a rough overview of our facilities in India. This is the only slide I have on the company at the moment, so that we save a lot of time and go into the technology part. But just to show a rough overview, on the top left, in Gujarat, we make resins. Yeah, the resins are basically organic polymer beads, which have a variety of applications. Just for example, a lot of medicinal capsules that people consume today have resins as an excipient, in which the active pharmaceutical ingredient is coated, and then you consume it. Yeah, so that it gives you an idea of what kind of facilities are required for manufacturing such products. And of course, these resins also used in the water and wastewater industry for specific absorption, ion exchange kind of applications. In Maharashtra, Rabale, we have an export-oriented unit, which is exporting equipment and products, like I said, to Europe and Middle East, America also. In Goa, we have two facilities. One is a plant which manufactures equipment, assembles kits for membrane systems. We also recently started a membrane manufacturing facility. It's one of the first plants in India, which is an integrated facility, where we start from liquid chemicals and rolling out, out comes membrane modules, RO membranes and ultrafiltration modules. So this, gives you an understanding of the capability of the company in terms of really creating products made in India from, basic raw materials. Then in Hosur, we have a large facility for engineering equipment. In Hyderabad, Patancheru, we have our chemical factory where we make a variety of chemicals for both water applications as well as for non-water applications like fire site chemicals, anti-clinker agents for boilers. Of late, also disinfectants we started making for industrial use, and there's a very, very strong chemical engineering team available there, which have their own R&D, develop products. And in Wada, in Maharashtra, we have a facility for making extra large size equipment. Yeah, so that gives you a rough overview of the company. And like I said, we are about 55 years old today, very, very active in the Indian market. We can go to the next slide. So now we get into the a portion of the presentation where we get the basics, so that everybody is on the same page when we start getting into the more technical aspects. So conventional treatment, where there is raw water coming on the left hand side. There is typically a water treatment plant which brings the water to a certain treated water quality, which is then used in the process. The process, it could be used for washing certain things or used in the manufacture of certain products. And of course, after the process, out comes effluent, which has got water and the other waste material coming in from the process, which goes into the ETP and it gets discharged. So this has been a typical, approach, conventional approach. And whereas what we are looking at today is a process where we are trying to basically ensure we recover all the possible water out of the effluent stream, number one. Number two, in the waste stream, there is also valuable material. Yeah, so we are trying to recover the waste, let's say the recovered product also out of the waste stream. Yeah, and then with the recycled water, we can reduce our water consumption, right? The raw water consumption. So basically, we are with all this, we are lowering our complete water footprint. The amount of raw water that we use is reduced. The amount of wastewater that we discharge is reduced, or at least minimized to the maximum possible, and also made as safe as possible for discharge, because we are also trying to remove all the contaminants out of the water, and wherever possible, even reuse the product. An example is, for example, in the textile industry, where salt is used in the dyeing process, and so far, there was a process by which we were recovering water and concentrating the waste. And off late, what's happening is, if you are able to process that waste salt in an intelligent way, then we basically can recycle all the salt back into the process itself and reduce your salt consumption for the whole dyeing process. Yeah, so which means not only are you reducing the water consumption, you're also reducing the amount of salt that is used for the fabric dyeing process. So there is, of course, a tremendous benefit, and the environmental damage is, of course, completely eliminated, because we are not sending out anything out of the plant. So this is the way the textile industry is moving, and I mean, a lot of industries are catching up very, very fast, and zero liquid discharge is here to stay. Initially, when it was introduced, I mean, 15, 20 years ago, there was a lot of wonder on how that can be done. But today, we are in a position where several good examples are there all over the country. Almost all major players are getting into this area, and I believe India is also one of those markets which is setting a world standard in terms of applying zero liquid discharge principles and applying new ideas and technologies to to get there in a variety of industry. So this being the overview, let's get into the next step, where I take you a little more deeper into the process. So, I mean, a lot of us are familiar with, a simple sewage treatment plant. Most of us have such a facility in our apartment complexes. We understand the municipal sewerage system. It's a process where there is a collection network. It comes to a sewage treatment plant, where the typical process is about physical separation of inerts, sand, stones, other larger items come out. There is an equalization tank where the water is stored for some time, because the flow is not uniform. Typically, in a municipal setup, you have a lot of flow coming up in the mornings when everybody gets up, has a shower, and gets ready to go to work. And then during the day, there is a slight reduction. Then again, it picks up in the evening. And then again, in the middle of the night, there is hardly any flow. So to equalize that, to normalize that flow, there is normally a facility in the plant for equalizing. And then it goes into the treatment process, a biological treatment, where the bacteria is made to work on the sewage water. Then there is secondary treatment where it settles down, the bacteria is removed, and the water becomes that much more clearer. And then it comes to a tertiary filtration, then disinfection, and then it goes out into reuse or discharge. And of course, as most of you are aware, in Chennai now, we are also getting into the plant where this water is polished with ultrafiltration or reverse osmosis, and then taken back into the industry for processed water use. The sludge stream, that is the solids, the pink box there, is again handled in a variety of ways. Waste to energy is one option. Yeah, stabilizing and disposal of that sludge is another option. And of late, there is also an idea to extract nutrients from the water, phosphates and potassium kind of stuff is recovered out of that water. So there is also a process for nutrient recovery happening there. This is the typical sewage treatment process. Yeah, and when you come to the industrial side, it starts getting a lot more complicated. So variety, first on the left-hand side, the industrial effluents are like what Mr. Bhaskaran was saying. It's a fantastic variety of effluents you have. And, conventionally, earlier it was all getting mixed up into a common effluent treatment plant, where you had a physical treatment where again we removed off the grits and food oil grease, that is FOG, that is mentioned there in the pink box in the bottom. Sometimes when you have upsets in the facilities, you have very, very strong effluents coming in. So these cannot directly be taken inside. So you need to store it somewhere. That is what is called this diverting of offspec. So you have a couple of storage tanks where something, there is a process upset or there is a plant, trip or something, and a lot of effluent suddenly flows into the CETP. You divert it off into a particular tank, store it, and so you can slowly take it into the main process. There is a physico-chemical treatment. That's the first step, because effluents have a variety of organic and inorganic contaminants. They also, so this is a very, very crucial process bit in handling that. The effluents could be alkaline, could be acidic, could have certain heavy metals, could have a lot of contaminants which are not easily handled by a biological process. So we try to remove all that in this physical chemical treatment, where a lot of adjustments are done post that to make these particular water suitable for the biological system to handle. Yeah, the biological system again is based on bacteria, and they have a certain limitation in terms of how well they can adapt to changing, input parameters. Yeah, so to avoid the bacteria from getting washed away or from getting absolutely upset, we have a strong, very strong physical chemical treatment done to make sure the water which comes into the biological system is well within parameters. And again, there is a process. If the water has got a very high amount of, organically degradable contaminants, then we have anaerobic process handling it. Or if it is not so strong, then we have an aerobic process handling it. And then, of course, like a municipal system, there's a secondary settlement, then filtration, and then water for reuse. But of late, what's happening is this effluent, which is coming out of the plant, is we are trying to concentrate that. So basically, we're extracting out, like I said earlier, maximum water out of this effluent as possible. And this concentrated effluent is what is taken into a zero liquid discharge, where again, there are a lot of technologies in the market coming up today, which have a very high efficiency in terms of extracting water. And if we are able to intelligently manage the process, we can do product recovery in several places, depending upon the kind of effluent which comes in. It might be possible for us to recover. For example, if there is a lot of oil and grease coming in, that could be recovered in the first step of the process. Let me take an example of machining centers, machine shops where a lot of machining is done on automobile components, for example, where you have coolant oil and water mixed, and this is an effluent which comes out. Now, if you are in a position to basically separate out the water and concentrate the coolant oil, this can be taken back into the process again. So that is like a product recovery out of a waste stream, where you reduce your initial consumption of coolant oil, and also make it easier for the ETP to handle this kind of emulsified oil streams. That is again a challenge for effluent treatment plants. Similarly, as long as you're able to, segregate the waste streams well, we are in a strong position to apply a good technology for recovering the product or recovering water or doing both, or making it easier for the effluent treatment plant to handle it. Yeah. So this gives you, a rough idea of how the challenges are split. In a typical municipal, we are talking about quantity of sewage coming in and quality. Typically, if it rains, a lot of rainwater enters the sewer system. That is what now Chennai is trying to resolve with stormwater drains and rainwater harvesting, trying to keep the sewage system independent of stormwater. But again, the quantity, as long as the plant is being fed the designed quantity of water and quality of sewage, it is able to work very well. The minute one of them changes, you have upsets. On the ETP side, on the effluent treatment plant, we have to be worried about a lot more things. It is not just the quantity, there is a variety of waste. When the waste come in, the timing, because not all plants produce the same thing at the same time. There are different industries or different processes running. Each of them might discharge their effluents at different points in time. Yeah, so that is something we need to consider. And then manufacturing upsets. When the plant has a problem and there is suddenly a dump happening, how do we handle that? So these are the things that a typical ETP plant operator needs to worry about. Yeah, and when we come into the the whole analysis of the wastewater effluent system, we look at it from, let's say, three perspectives. The first one gives you the first, let's say, the orange box talks about the challenges that we face. Typically, this is what Mr. Bhaskaran was talking about. Every waste stream is valuable. The minute we mix them all up, it becomes a huge challenge. As long as we can segregate the waste streams, and identify, study them, there is always somebody who will find that waste stream useful for his manufacturing process or his production. Yeah. So as long as we are able to consistently deliver a particular waste stream of a certain quality, it can be made use by somebody else. Yeah. Then again, the second point on the orange box is the characterization. COD stands for chemical oxygen demand. TDS stands for total dissolved solids. So these are a couple of parameters which determine how the plant has to be designed. So the minute we mix up a couple of these streams, it becomes very difficult for the ETP to be optimally designed. You might be able to still run the ETP, but efficiency will take a hit. Yeah. Then there are certain non-biodegradable chemical oxygen demands which need a very, very strong chemical reaction to break down those those kind of complicated chemical molecules, benzene based or certain new generation long polymers. Yeah. Then, of course, could be contaminants, heavy metals. Heavy metals have a big impact on the bacterial, activity. So, and also, difficult to remove from the water stream. So, how can we remove it off initially itself? And then certain streams have a lot of color growth. I mean, textile dyeing was one industry, but you also have other industries where certain chemicals impart color to the water. And this again has an impact when you discharge such water, into a general waste, into a general water body, a lake or a stream or a river. This, while the water itself may not have any harmful contents, the color of the water, prevents sunlight from penetrating into the bottom of the water body, and thereby it starts creating a lot of other issues for the organic life there. The plants underwater or the microorganisms don't get enough sunlight, the fish don't get sunlight, and then it upsets the whole ecological chain there. So that is why these color streams also are very critical. So in terms of prevention concepts, the middle box, talks about understanding the material processes. How is the manufacturing happening in the industry? What kind of segregation is possible of different waste streams? How can those systems be designed? Yeah, is it possible for us to make some changes in the manufacturing process with respect to the wastewater focus? This is becoming a very important process in redesigning how factories are made today. Earlier it was all about production speed and how much throughput we can achieve. But today, this what kind of waste it generates, how can we optimize that? How can we make use of this waste for either an upstream process or a downstream process? These are the things that determine now the latest production flows in industries. Typical example would be, like, say, automobile paint bath systems. From what was designed 15, 20 years ago, what is designed today is a very, very different process. Where they talk about recovering all the paints that is used instead of washing it away to the ETP, and making sure you reduce the paint consumption and also the water consumption in the whole painting process. Yeah, operating practices again, with respect not only for machine uptime and production, but also with respect to waste minimization. So these are things that are increasingly being focused upon. Then water audits, and the second point, review of just one second, Vivek, so water audits is a very, very crucial aspect to be taught about, because a plant which was designed 10 years ago might not be having the same loads today as what was foreseen 10 years ago. So only when we do a good water audit are we able to understand how the ETP is working and what needs to be changed today. And in terms of technology, there's a lot of things that has happened in the IoT area with respect to remote monitors, auto dosing systems, how to get data to a remote expert who can then diagnose the fault from far and then give recommendations on how we can solve those problems. Recycling, reuse, we talked about. Reject management, we talked about. And the product itself getting changed. In terms of now packaging industry, as IWMA will be very well aware and probably drivers in this. How do we shift from using plastic for packaging to paper? What kind of instead of using bubble wraps, we are using crushed paper, for example. That completely changes the way the packaging industry works now. Yeah, that's again environmentally sustainable, and paper is far more easier to recycle. And this craft paper business is picking up in the country because of these kind of sustainable practices. Then what is the benefit that we have out of all this? Of course, we are going away from seeing waste into reducing costs and looking at the waste as generating more profits for us. Production of fresh water is again a finite resource that, as long as we can reduce that, it's always a good thing. And of course, a lot of other points come up. Yeah. So let's go to the next slide. Yeah. So I just will have a quick case study. All of us have been in the post-COVID situation, spending far more time in the kitchen, I guess. So I thought I would take an example from a large-scale kitchen that we're able to relate with the kind of effluents and why this effluent analysis becomes a critical topic. So this is the data from a kitchen that we recently studied. They have the initial data that came to us was they have a problem with their STP with the 200 KLD, 200 kiloliters per day STP, which was handling about 50 kiloliters of sewage and about 150 KLD of kitchen wash water. So, but they have a big problem. Yeah. And typically what we know is all the load is organic. There is no heavy metals. There is no harmful stuff here. So these are all easily biodegradable stuff. So why should there be a problem? Yeah. So the way we go about it, is something called composite sampling, where we look at the waste streams every 1 hour. We take a sample and mix them all up, and then try to get a composite sample of complete representative sample of that particular load over a period of 24 hours. Now we look at the flow patterns. Weekend load. This is the kitchen which was supplying food to schools, so which means they stop operating in the weekends. And so Monday morning peak load, and then of course Friday evening the load goes down. The kitchen stops for Saturday and Sunday. Again, schools have summer breaks, so which means 2 months in a year the kitchen is not running. So what happens then? How is the plant working in those days, and how does the plant start up again once the long break is over and immediately the kitchen comes back into operation? Yeah, what are the daily peak flows? What are the peak biological loads? This is the study. Yeah, and then what comes out of it is something like this. Can you? Yeah. So this 200 KLD, is broken up into all these different streams. So all of us now with experience in the kitchen in the post, in the COVID days, we will look at, this is typical stuff that we all do. We wash the rice. There is dal is a part of the meal that is also washed. Then the rice starch is removed. The kitchen is washed every day. After the cooking is done, there is the floor washing. Then vessels come back. The vessels are filled up, so vessels are washed. Yeah, and vegetables are washed at a certain time. So this is the process flow they have, and all these different flow volumes. And those yellow boxes. Can you go to the next slide, Vijay? Gives you an idea, of all the different loads. TSS is total suspended solids, TDS is total dissolved solids, COD is chemical oxygen demand, BOD is biological oxygen demand, just to give you an idea. So the different flow volumes, and what kind of contaminants they have in those is what I have kind of highlighted. So the original concept was to mix up all this together and treat. Yeah. And this, of course, is not sustainable, because once you design a plant for this kind of loads, you're looking at look at item number 5, for example, total dissolved solids. Yeah, 13,790 is one parameter, 30 kiloliters per day. And on the right extreme, you also have the sewage plant, which only has 400. Yeah, and again, the sewage plant is going to be operating more or less continuously because the staff will be there all through. Whereas the starch water will come only on 5 days in a week. So if you design something for handle this particular load, it won't work for the other 2 days. And if you design something which will work for the sewage, it will not definitely handle this kind of overloads, because every system has got its own design envelope. You can ask it to do 30% more, 50% more, but this is something like 2000% more, right, in terms of handling loads. So the whole waste stream, you need to understand it and then figure out what's the best way to handle it. So can you go to the next slide, Vijay? So ultimately, end of the day, can you go back one slide? So end of the day, the recommendation, how we look at it is this high strength starch, the 8 AM 30 kiloliters, which is not a huge load compared to 200, but it has got a very, very high hit on the impact on the whole plant. So this stream had to be taken separately. Yeah, and this would possibly go through an anaerobic process where the process is designed for handling that kind of stuff. The STP, the sewage on the right hand end, would be handled independently, because that is a continuous process and it can be optimized most. And all the rest of the water, the rice wash, dal wash, the floor washing, all that could be combined, and we could still have a reasonably compact system handling that. Yeah, the minute we try to mix up the starch water in that or the sewage water in that, you have a very sub-optimized system which will not work, because it simply cannot handle such extreme variations. So this kind of gives you a rough overview of how effluents need to be really categorized very carefully. Yeah, can you go to the next slide, Vijay? Yeah, so that is where the water audits become a very, very important portion. Again, people like IWMA, CII, and even we as a company do water audits. Where the expert, when this comes out of a lot of experience, multiple disciplinaries. It's chemical engineering. It's understanding membrane processes, what can work most effectively for this effluent. So this kind of a team, once it studies the effluents available in the plant, yeah, and also understand performance issues, they can probably give a much better recommendation, a good design which can handle all the variants. The second important point is flow metering. A lot of us, estimate flow based on our gut feeling. A pump is running for 3 hours, it is going to discharge so much of water. That could be probably the basis of the whole flow, audit itself. This again is True, but more often than not, the pump's performance changes with a lot of parameters. What is the head? What is the kind of scaling on the discharge pipe? What is the level of water in the suction tank? All of it determines the flow output of the pump. So, and traditionally the flow metering was a costly subject because the flow meters were expensive. But today we have a lot of technology with clamp-on meters, temporary meters. You can get someone to come and fix a couple of meters, do a flow audit for 2-3 days, 1 week, and get a very good, accurate map of the whole waste stream coming from different units in the facility. Either it's a single big factory or even multiple facilities, multiple factories coming to a common effluent treatment plant. You can do a good flow audit, which will give you the volumes, very good, accurate prediction of the volumes. Yeah. Then looking at, this also will tell you, where are the leakages happening? Can we plug those leaks to reduce the total generation of effluent stream itself, and also reduce the freshwater intake. Zero liquid discharge again becomes a mandatory topic these days for certain category industries, and that has to be explored. And whether it is possible for us to see a return of invest on that. Will putting a zero liquid discharge really save money for the company? Yeah, because the cost of sending water to a common effluent treatment plant, and also losing this, let's say, the waste in the water, which is actually a resource. Often with the cost coming down on the zero liquid discharge, this becomes a opportunity also. And looking at upgrading the existing facilities and then bringing it up to date. Yeah, so this is what a water audit would normally come out with. So now I will hand over the session to Vijay. If there are any questions, you can post them on the chat window. We will keep a track of it, and we'll try to answer it as in when we Vijay, I can see that there were some questions there. Maybe we can take a few before we go to the next session. Vijay, I saw, yeah.
Okay. So should I read out the
question? You can read out. You can read out. Thank you.
Okay.
Sir, I will read for you, sir.
Yeah.
What will be the criteria for the product recovery from effluent, looking at economics involved?
See, this I mean, it's a very generic question. For us is how quickly, how easily can we segregate it from the water stream? So if it is only a single contaminant in the water stream, like I said, these the coolant oil recovery from automobile machining shops, where they are machining centers or lathes or drilling units are producing automobile components. The contaminant there would be typically metal chips, and coolant oil, emulsified oil. And this, we will talk about certain technologies, are very easily separated. Yeah, in a single step process, we can do that. Yeah, so cost, of course, is the criteria. Yeah, but again, the cost is, you need to evaluate the overall cost in terms of the cost of treatment and the cost of disposal of this particular effluent stream, because once you start recovering the product out of the water, you also don't have a disposal cost. And when you look at an overall evaluation of that, you would come up with an ROI calculation. Minute the contaminants start getting mixed up, yeah, with 2, 3, 4 kind of effluents getting mixed up, then it becomes a lot more complicated to remove it. So that is why now we are trying to move the whole ETP from a centralized kind of facility to more decentralized, where each process unit is looked in isolation, and then we are seeing whether we can do something locally itself, and then recover the product or reduce the generator. I hope that answers the question. We take the next one.
Yeah, sir, I think we can have the Q&A session at last, sir.
Okay.
We can finish the PPT.
Sure. Okay. So
yes.
Then I will ask Vijay to take over. And
yes, sir. Yes, exactly.
Thank you.
So welcome, Vijay, sir.
Yeah, thank you, Mr. Mahesh and Vignesh. We'll be looking at a little more detail about the products and technologies based on the effluent which are generated. Now on the slide, you probably can look at the the typical effluents which are basically total suspended solids, and the oil and grease are heavy metals, and also organics and colors. This basically comes from any kind of industry, starting from textiles to automobiles, or maybe the pharmaceuticals. Okay, So the important front probably here is to analyze these particular effluents, with a detailed analysis prior we take up, the design of particular, water treatment plant or a wastewater treatment plant, because the performance of this particular plant decides on the proper sampling and the analysis of the parameters what have been, specified here. So I have a difficulty in changing the slide. Yeah.
Vijay, shall I take over?
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
Yeah, a moment, please. Yeah.
Yeah. Okay.
Yes, sir. No
Okay.
worries. Yes.
So while Ms. Mahesh has just emphasized on the the types of technologies are the steps to achieve zero liquid discharge, I would like rather to spend it on a step by step in terms of primary treatment and the biological systems, and also the tertiary treatment plants and the reject management, of course, to achieve zero liquid discharge. Now, basically, the primary the primary treatment is one of the important step or prominent step to achieve zero liquid discharge, because here you're going to you're going to control the complete downstream performance of anaerobic process or a tertiary treatment, even the downstream, particularly in terms of the saving the OPEX cost of a particular design. In the primary side, what we look at is ceramic filters, basically, where we look at for a product recovery, and the advanced clarifiers in association with the the existing conventional primary clarifiers, and followed by a laminar clarifier or an HRSCC, with UHRCC as being one of the advanced clarifiers here. The DAF is one of technology which plays an important role in removing this the emulsion oils there. The advanced oxidation systems, the electrocoagulation systems, which constitutes about the primary treatment. In the secondary, we look at which is more a biological systems. We look at the USBR technology, where it is advanced towards tall reactors, and which is also integrated with the waste to energy systems. The aerobic process constitutes morely of a MBBR technology and membrane bioreactors. These are the advanced technologies in association with the extended aeration systems, or maybe with the sequential batch reactors, which are fully automated using a decanter system. In the tertiary, which is more of using the water post discharge. Now, what happens in a public municipal sector or in industry, the water basically is treated to up to a level of discharge. But then the tertiary plays a major role in saving the OPEX cost, because you are going to use this water into the process, and your into your direct cooling tower makeups, or for any other direct use in terms of the in the process for manufacturing. So here in the tertiary, we will look at products which are more innovative, like ORC media, disc filters, and we'll see the self-cleaning filters. In association with the membranes, we are also looking at something more advanced related to EDR technology or a forward osmosis, the disc and tube technologies, which are parting in the tertiary treatment there. The zero liquid discharge, which is a final concept, what we talk about, getting the salts out of the concentrated liquids which come from the RO system. Here there is a development on that, but I think the last step probably needs little more work around to reduce the the concept of the OPEX there. Otherwise, the conventional multi-effect evaporators with TVRs and MVRs are playing a major role in doing the zero liquid discharge process, and further ATFDs and the centrifuges for the salt recovery. So when we said in the primary, we are all sure and thorough with the process that there are like screenings, grit removals, oil removal, these are the prime steps, and further the clarifications. So one important in the oil part is to concentrate the coolant oil, or the oils at at the beginning, where you recover this oil with the help of ceramic filters. I'll just show you in the next slide how the ceramic membranes do the role of oil concentration. In the sedimentation, clarifiers and the primary clarifiers have played a major role, where you try to do the pH corrections, heavy metal precipitation, and also to remove the suspended solids to a great extent, so that the downstream biological system doesn't hinder in terms of performance. Okay. In the clarifiers, we'll look at the lamellar clarifier or the HRCC. UHRCC is one of the advanced technologies here. The ceramic membranes basically, are having a MOC of silicon carbide. The silicon carbide gives the membrane kind of more toughness, where it can resist up to 800 degrees centigrade. It operates the pH range, in the 0 to 14 kind of a range, and high flux rates can be drawn out of this, where you can go up to 300 LMH. In terms of the permeate, what you get out of the particular membrane surface. The fouling of this particular membrane is very low. That's how it becomes a more high performance membrane system. Okay, so the applications, what we said earlier was, if you wanted to recover a product which is contaminated with oil, and you would like to recover that oil and concentrate further for reuse or for further sales, this membrane can be used. Okay, so in recovering the high metals, heavy metals, also the ceramic membranes do play a role. And of course, the basic function of any kind of ultrafiltration kind of a membranes is to remove the colloid particles and also TSS from the pre-treatment, and they're used as a pre-treatment. Okay. So when we talk about the clarifiers, when we have to look at the ultra high rate solids contact clarifier, we must have to little more understand the basics of probably the lamellar clarifier, how the performance of the lamellar clarifier is achieved with a rise rates of about 1.3 meters per hour. Okay, so on the right side you see a picture which is a typical lamellar clarifier. The raw water, or the water which need to be treated, has to be pumped into a SMFT, which is a static mixer flocculation tank. In this particular tank, we are going to add flocculants and chemicals, the coagulants, so that the particle formation is made heavier, so that it further settles down into the lamellar plates. Now the lamellar plates have been inclined in this particular slots at about 60 to 70 degrees, and they form as an inclined plate technology, wherein the water in the lower picture you can see the water will rise on the plates, on the surface of the plates, and the heavy metals, I mean the heavy particles whichever has been agglomerated or flocculated, try to settle down at the bottom of this particular hopper, and the clear water comes out of this. So lamellar clarifier is a proven technology existing for last 50 odd 20 odd years in the Indian context, and maybe in abroad probably it is there for a very long time. So the second clarifier we look at is the high rate solids contact clarifier. This is taking over the conventional clarifiers, where we talk about clariflocculators, where the flocculation zone and the coagulation zone is outside the this particular outside the premises of the clarifier. But within the HRSCC, there is a draft tube which is inside the the clarifier. The chemicals are dosed in this particular zone here and given a retention time, and within a very short time of retentions, you will achieve a good flock which overflows, and then it is collected at the bottom of the tank, and the clear water comes out with rising up to around 3.6 meters per hour kind of a flow rates at the velocities you have in a typical HRSCC. So yeah, I think we'll spend a little more time on this particular thing, which is the current updated technology, where it takes over the advantages of a lamellar clarifier and HRCC. What it does is it integrates both the things into one single system. The raw water is pumped at the bottom of the tank to bottom, and then it is pumped into the draft tube. This particular area is a draft tube, where the polymers and the coagulants are being dosed from the top with the drive on the top, and it's continuously agitated. In the process, what happens, you get the continuous flocks of a heavier size, which you try to settle down at the bottom, and you get a clear water which is deflected and passes through the lamella plates, what are inclined on the either side of the the draft tube. So you get a clear water when it comes to, in terms of TSS or, in terms of turbidity, there is a good control. Now, what makes the ultra rate, solids contact clarifier a more advantageous product is that it can, the rise rates, in this particular clarifier goes up to 15 to 20 meters per hour. Now, why is doing so, the chemical consumption compared to a normal clarifiers will be saved up to 15 to 20%. And the energy, energy, the footprint, or even the, the overall operational efficiencies are improved in a ultra, a high UHRCC. So where do we find these applications are in a lime, lime softening process, removal of colloidal silica, color removal in the industry, white water recycling, or maybe for, the heavy metal precipitation. So once probably you get, a proper, treatment out of this, probably you can achieve up to a TSS less than 15 ppm. So that is very significant, when you see operational performance of a clarifier, even in turbid conditions. So from primary side, we'll move into the secondary. I'm sure I need not to introduce the basics, of this particular thing. Still, we'll look at what are we trying to achieve. In the secondary treatment, we try to remove the, organic matter via oxidation of, microorganisms, in a natural way than using any kind of a toxic chemicals. So COD, BOD are the familiar, terms which we are going to use, where we would like to, remove this particular stuff with a bacteria growth in the reactors. Yeah, in the anaerobic, digestion is being existing for a very long time. So so USBR, where the COD loads are, very high, and you would like to, get the energy without, I mean a biogas without spending any kind of, external air. Anaerobic process play a major role there. So here we will be, looking into a tall reactors in the slides to come. In the conventional, we said, we look at the fluidized media reactors and the MBBR technology, which will be having a performance where the water becomes absolutely to a standards of drinking. I mean, that is how the MBRs perform. These are the conventional, USBR reactors. What ion exchange, in the process has done is, see, this is a picture of a typical USBR reactor. So while there were a lot of, drawbacks on the conventional design in terms of distribution, in terms of the, the gas which has been collected, the biomass separation, or the corrosion within the, reactor. So ion exchange has ensured that all these parameters like the corrosion with respect to change of the MOCs from MSCP technology to moving into FRP was done, and the distribution was done through a top from a top distribution system where the water is introduced to the bottom of a tank. So the anaerobic reactors, basically the function is ensuring that there is a continuous feed throughout to the complete surface. Now, what we found out was in the normal reactors, it was clogging because of the pipe distribution system available there. Yeah, this is a state-of-art kind of technology called tall reactors. The conventional the reactors had a lot of setbacks or the performance issues in terms of digesting a high COD levels. Now, a tall reactor can handle up to 35 kgs per meter cube per day kind of a volumes there in terms of COD. What is done is the water basically can travel up to a 25 meters kind of a reactor, unlike a conventional reactor. So the water is introduced at the bottom of this particular reactor with a fine distribution system, and it passes through two different separator zones where the gas and the biomass is separated out very efficiently. The biomass is returned in the bottom of the tank, while the gas is collected into the next chamber, which is called a neutralization pit. Now this makes the anaerobic reactors different than the existing reactors in the conventional market. So the USBR or the ECSB technology has a neutralization pit which collects the biogas from the various parts of the reactor of the ECSB and the complete gas is under pressurized, so that there is ensuring that there is no leakages. So the corrosion in this kind of a reactor is also minimal, because there is no external air has been provided, or there is no chance of any kind of slippage of a biogas also. So the efficient of this particular reactor is that you can feed up to, as I said, 35 kind of kgs per hour per meter cube, this particular COD, and you can achieve a very significant, where the downstream has to handle a very small loads. Okay. So in the aerobic treatment, we have the fluidized media reactors, also moving bioreactors. Basically, the media is suspended. This is a typical MBBR technology, where the water is collected in the collection tank and is pumped into an anaerobic zone 1 and zone 2, where the media is suspended, and with the retention time about 1 to 2 hours, the water is absolutely treated for the the COD and BOD, and eventually it passes into a next level of treatment using the lamella plates as a technology. There are also multiple ways of doing it, but then we felt that this particular plate technology is easy to clean. So the water rises above the plates and then comes into the chlorination zone, where it is further sent for a tertiary treatment. The media which has been suspended has a good surface area for the bacteria for attached growth. The high rate MBBRs are something more significant for industrial wastewaters, while the MBBR basic MBBR technology has a limitation on handling the the industrial effluents. It was more for the sewage treatment plants. But when you look at high rate MBBRs, the media which has been used inside is a highly porous media with carbon impregnated substance on that, so that there is the absolutely porosity, and the absorption of the COD or the BOD on that particular surface is also high. So it is it's like an attached and suspended growth process. So it's a hybrid technology, further reducing the performance. Improving the performance and bringing the foot size of that particular reactor. What's the best part about this particular reactors is the downstream will be absolutely having low levels of COD in terms of discharge or in terms of our reuse. So now,
perhaps just Vijay, I'll just make one point here in the earlier slide. See, in a typical MBBR, what Vijay talked about one slide before. Yeah, so here it is mainly an aerobic bacteria that is operating it. Yeah, whereas in the high rate MBBRs, what's happening is the microbiology is far more sophisticated. Yeah, can you go to the next slide?
Yeah.
So in these kind of media, within each of those plastic, let's say sponge-like media, you also have the outer surface is a high oxygen surface, and inner area of that sponge becomes a low oxygen surface, where different kind of bacteria are able to operate within the same tank itself. And that is the trick, or that is the key difference with respect to how the whole process operates. So superficially, it all looks the same. In one place we use a plastic, kind of a disc or something, and in another place we use a plastic foam or a sponge. But the way the microbiology works is very, very different. Yeah, and so this is where this whole ETP topic is a multidisciplinary topic. You're talking about chemical engineering. A lot of microbiology is coming in, and off late it is getting even more sophisticated. The same story also with the tall reactors, anaerobic reactors. The whole microbiology there in terms of the kind of sludge that develops on the reactors is very different from what we were generally used to the last 10 years. Yeah, back to you, Vijay.
Yeah. I think we have a success of this particular with a project at a century range. So that is how we felt that this particular thing can be more useful for the aerobic treatment systems compared to the extended aeration or the secondary clarifiers. So we'll move to the membrane technology, which is one of the sophisticated thing, in the treatment of both sewage and also the industrial wastes. So for quite long, the tubular and the hollow fibers are the flat-sheet membranes are in the market. But let us before we move into the the ones which ion exchange is looking at is the IPC membranes. For the concept, the membrane is something which will be worked upon by I mean in a particular process of handling the sewage water. The water is subjected to the anoxic treatment and then aerobic treatment, and further it's sent into an external MBR, where the membrane acts as a physical barrier for suspended solids and also the viruses and the bacteria, and the clear water is sucked out from the membrane surface. So how MBR makes a savings when we look at a conventional process or a ASP process? It cut down on a lot of equipments related to aeration, clarifier, recirculations, the tertiary treatment, and further polishing of that. So an MBBR an MBBR technology is superior, but then the MBR further exceeds the performance of the MBBR technology. So when we look at this, this is also existing in the Indian market for almost now 15 years. But yet there are a lot of issues in terms of fouling and the flux rates and the issues related to the performance of the membrane and the life of the membrane coming down. So in order to address that, the challenges, ion exchange has tied up with a company which is working on both a joint venture for developing a specific membranes called integrated permeate channel membranes. Now these are membranes which basically are a flat sheet membranes where it's like a net, what do you say, a textile coated network, where the membrane is pasted on the surface, and the internal the structure allows for a lot of in terms of the removal of any suspended solids, it acts as a barrier. Okay, so by improvement methods, what are we looking at is we would like to increase the flux rates as high as 40 to 50 LMH and reduce the transpressure membrane pressure. So the TMPs are up to 2, so where the membrane cleaning is easy and the membrane ruptures are very minimal, and you get outlet performance up to BOD levels up to almost 2 ppm. So that's the level of achievement when you have it in form of a MBBR. Yeah, this is a site installation of an MBBR at a pilot location. So what we found out was the BOD levels are achieved up to 99%. The phosphorus levels are also to the minimum. So the nutrient removal is also possible when we go through this particular process. So the coliform bacteria is a 6 log reduction to get the pure water as high as as a pure clean water for even for drinking purpose. Of course we don't recommend it, but then that's the quality what you get out of a IPC membrane. The electrocoagulation systems are also finding its application for the COD, BOD, nitrogen reduction, and they basically also are handled as a pre-treatment equipment in the oxidation systems, where the downstream process equipment size can come down, and further you have saving on the operations are minimum. When we talk about the solid waste, activated carbons been there for very long doing the dechlorination activity, and also for but they are also adding as a solid waste. So what we look at is an ORC media, which is a typical media, kind of a glass beads which are replacing the activated carbons. The performance of this particular thing is that it can go up to 2 years as a performance, so that you have to reduce on the solid waste disposal costs, as well as the impact on the environment is less when you go for ORC. Yeah. So in the tertiary treatment, which comprise of the continuous sand filters. The sand filters basically, this is a self-cleaning filter where the COD and also a portion of the nitrogen is also removed with the sand continuously in clean in process. So there is no stoppage of the filters for a backwash. The filters are continuously recharged with the sand media being present in the same thing. You are not removing the sand for a separate cleaning system, or even allowing the filter on a continuous or a 24-hour operation for a optimized performance. The ultrafiltration and the RO membranes have been used in the tertiary treatment for a while, but we look at the next level of the RO membranes in terms of disc and tube. The disc and tube membranes can take up to loads of the COD of around 5,000 and can handle as high as 50,000 TDS levels. So the in a normal spiral membrane, RO membranes, the chances of the COD of not more than 100 ppm is allowed, but in this case, when you can go up to 20 or even 25,000 ppm, the COD levels are handled in this disc and tube RO. So currently these installations mostly are found in the the Indian ships or the submarines, where the disc and tube RO plays a major role. But in the textile applications and also leachate thing, we are seeing that the membrane related to disc and tube are replacing the spiral wound membranes. FO is a latest addition to the the RO reverse osmosis systems, where a high TDS water up to 70,000 ppm can also be addressed to a a membrane where the exchange happens with low energies. For example, if you look at the desal membranes, they go up to pressures up to 60 kgs, wherein you get the you get a permeate about 400 ppm to 500 ppm, but then you see the energy cost there is about I think it's a 3 kilowatt per hour or per meter cube is the consumption there. But so to address the issues related to performance of a high TDS waters about 70,000, so FO plays a major role. So yet we have to get some kind of a pilot plants for this, but its trial is in process. So the zero liquid discharge basically talks about the taking the RO rejects and further getting into a kind of the condensate waters and also the salts, which we achieve through using a force circulation evaporation. Okay. Hello, Mahesh, I'm not able to move this slide.
One second, I'll just repeat. Are you able to see it now?
Yeah.
So
yeah. So in the to achieve the zero liquid discharge, so normally for the wastewater treatment, we prefer to have something like a forced circulation evaporators, where the calendaria and the flash vessel are in the downward, the water is introduced, the wastewater is introduced at the bottom of the calendaria, and it is flashed in the next vessel. So this is a typical zero liquid discharge forced circulation evaporator. Yeah, further, the evaporators, the final step is to get the salt out using the ATFDs and the salt saturators. Yeah. Maish, I think that's the typical products what we have.
Let's take the questions now.
Yeah.
Yeah. So I'm just let me just.
So we can take 15 minutes, 20 minutes for the
Yeah,
Q&A.
we are really overshot. Yeah. So I don't know whether you can see this chat window on your particular screen. There's a question from Mr. Chatwal. Do you provide online monitoring stepwise for treatment and link to SCADA of processes? See, online monitoring stepwise, is definitely feasible. But I think it's more important to the online monitoring in terms of certain basic parameters is not too expensive to implement. You're talking about temperature, pH, conductivity kind of parameters are easy to monitor. But as we get into the more sophisticated parameters like BOD or COD or those kind of parameters, it becomes expensive. Yeah. So we are looking at of course outlet discharge online parameters. We definitely want to monitor as much as possible, including things like BOD, COD is possible today to get online measurement for those parameters. Turbidity is always possible. So these can definitely be taken to the SCADA quite easily. Yeah. Inside the process itself, I think we're looking at more specific, parameters. Probably pH, temperature, because pH is linked to temperature. So these two can come from a single probe and can be taken, and that can be used for several both feedback as well as feed forward process control. I think Ketan Desavi addressed this question regarding criteria for product recovery from effluent. I think it's mainly economics, and feasibility of availability of technology to do a very quick recovery closer to the point of discharge than in a common ETP. I think that's the general principle we are working towards. Impact of global warming from Mr. Chatwal again. See again, we have a direct impact on global warming by the amount, by the efficiencies involved. So if you're able to save on power, save on efficiencies, automatically it has an impact on global mitigating the effects of global warming. So as technology, we are not doing it, but for example, there are other large companies operating in Chennai municipal facilities where the whole STP is powered by the biogas that they are generating in the plant itself. So that plant is almost a zero power plant. Yeah. So this is a fantastic, reference in terms of how the waste itself is used to power the whole sewage plant. This is the way forward. Yeah. So that is where we come in. Yeah. And as long as we can, anaerobic processes, of course, will generate methane. But again, methane, we are consuming it as a fuel to run equipment and to develop, power for the process. So yes, we will not emit methane, but we will emit carbon dioxide. But I guess it is lesser harm than methane. So we definitely have a lower impact on greenhouse gases. Vadim Subhash Chandra Bose, new tech RO. So new technology RO. So ROs typically where we're looking at pushing water through a membrane against the osmotic pressure. Yeah. So we talked about earlier seawater membranes where we talk about 60 bar pressure, 70 bar pressure. We are pushing the water through the membrane. The newer generation of RO membranes, how shall I say? They are looking at reducing that osmotic pressure differential. So instead of working with very high pressures, they are trying to work with lower pressures. So instead of pushing water from let's say 60,000 ppm, or let's say seawater is 45,000 or 40,000 ppm into 400 ppm in a single step, they go from 40,000 to 20,000. So the osmotic pressure differential is much lower. So the lesser energy consumption is there. And then they go from 20,000 to 10,000. It's like a series process of low pressure membranes working across a lower osmotic threshold. Yeah, people call it countercurrent RO. People call it, there's so many different technology terms they use. Each of them is a patented process. But the principle is we are trying to limit the pressure differential across the RO membrane and also play with the chemistry of the membrane material itself that makes it easier for water to pass through and selective ions to be held back. TVRC is on an evaporator topic. It's a turbo vapor recovery compressor. So basically, it is we are looking at using steam for the evaporation, but at the same time trying to create a low pressure so that the water can evaporate without very high temperatures. So that equipment is used in that evaporator process. Please share about Subhash alerts IoT. See again the 10 years ago, we didn't have the variety of instruments, and also connectivity was always via cables. So today we are looking at cheaper quality, cheaper cost of instrumentation. So the instruments, the probes, and the communication devices have all become wireless. In fact, we even talk about flow meters today, which are battery backed, which work for 6 years, 7 years, 10 years, buried under the ground. Yeah. So we are looking at getting away from using a flow meter chamber and power supply for that. In remote location, you need to get a 11 kV cable on the electrical distribution system and then step it down to 440 volts for that particular flow meter chamber or for that water quality chamber. But today we're looking at instrumentation which works off batteries or which work off solar power, which are much more easier to install. And since you have mobile connectivity, you are able to get data without cables. Yeah. So minute you have that kind of an infrastructure in place, which is much easier, quicker to implement, immediately the intelligence that you have about the network goes up enormously. So if you're looking at a city water distribution, 10 years ago, you had 40-50% non-revenue water or water leakages. Today you distribute 50 flow meters across the city. You immediately get a good idea of where you're losing the water. And immediately you can work on those areas where you have the highest water loss or highest incursion of bad quality water into the main supply pipeline. So that's the way IoT is helping us. Yeah. Both with respect to the distribution of sensors and the cost. And more important is they are also able to do a lot of local computation. So instead of being constantly connected with the SCADA system, these IoTs are able to do some processing, pre-processing. So they send one message once a day with the whole day's data log, or they report only when there is certain exceptional conditions coming up, or they are even able to do some mathematical calculations and then report only when there is something deviating from the mathematical model. So those IoTs, that's the way it's going. Dewatering of sludge. Sludge dewatering. If it is organic sludge, you go with a certain process. If it is inorganic salts, we go with push centrifuge. It again depends on the nature of the sludge. But this is again a variety of equipment is available in the market. There's nothing very high tech there. And to enhance the dewatering capabilities, you might add some chemicals or some polymers, which would make it quicker and easier to handle. The idea is that we want to make sure the sludge is coming out with the least water content possible, and whatever chemical or physical means that we have for achieving it, we try to do that. The question from Mr. Subramaniam, EHS, yes, can we use sewage treated water for internal gardening purpose? Yeah, absolutely. I mean, when you talk about secondary treated sewage, PCB India has got certain regulations where they talk about where the water can be used depending upon the treated quality. So PCB norms give you that guideline. But what you need to be aware of is that if you are looking at typical, let's assume an apartment complex, where you have bore wells and you have an STP plant and you have garden where you discharge your treated sewage water. So this closed cycle can happen very quickly there, because you're also having bore wells where you extract water from the ground itself, and into the same ground on the top you're also putting your treated sewage water. So it's very important in those conditions to be sure that the plant is working very well, in terms of the contaminants which is going in the water, the biological E. coli load in that, or the total dissolved solids, or ammonia, nitrogen, nitrate, you have to be very, very careful about that. So yes, gardening is the first logical use, landscaping and gardening. Again, you need to worry about the STP quality and the the short circuiting of those particular groundwater pathways. I'm not seeing anything with conductivity versus TDS in the data shown. I mean, TDS is total dissolved solids. I mean, depends upon the kind of solids. If you're going to have organic stuff, it may not have too much of a conductivity impact. But if you're going to have salts, you will definitely have a high conductivity impact. So the TDS is a very generic term. It includes both inorganic as well as organic contaminants. Whereas conductivity, works only based on inorganic contaminants mostly. Ankit Kumar asked about wastewater from household. Recycled water can be used for construction work or for gardening. Yes, absolutely. Absolutely. That's the way forward. Complex effluents case studies. Okay, perhaps there's no name on it. We definitely wanted to share some case studies, but again, we were not sure of the crowd today, so we have kept it very generic. But please send us an email. We will have the email coordinates down below in the next slide, and then you can send us. How to stabilize STP sludge? Again, you got different ways of doing it. Drying it is the easiest way, but if you don't have space, then we need to add in certain chemicals, lime basically, to kill off the bacteria and stabilize the sludge. But of late, what's happening is the sludge is going into the anaerobic process and for generating energy from anaerobic process. So slowly we are going away from disposing of STP sludge into reducing that volume using anaerobic process, digesting it, and then it comes out as manure. So that is the way it goes. So putting in lime and stabilizing sludge is slowly on the way out, and more green way of doing it is through anaerobic processing. I will just, can you explain the dosage details in chemical treatment part like ppm calculated? Vijay, perhaps you can take that question on, how are you handling chemical?
See, basically, the load of, the TSS after the jar test decides the dosage of the coagulant and the flocculant in the flocculation tank. So prior, analysis of TSS and turbidity is important to decide the loading. Otherwise, what we see is, it ranges in between somewhere around 5 ppm to 15 ppm for a normal surface water.
Okay, so there are a lot of questions on, on the quantity of.
Yeah.
Go ahead, Vijay. Yeah.
There was, okay. I mean, in terms of the oil removal in the ceramic less than 10 ppm. So probably we are looking at high concentrations of oil, say about 10,000 ppm also can be concentrated in ceramic things. So less than 10 ppm won't be viable for using in the ceramic membrane systems.
Okay, so there are a lot of questions further. I think we are running short of time. It's now 12:40 already. I think we have extended by almost 40 minutes. Apologies for that. I will just go to the next slide where we can make a note of our email IDs and contact numbers. So and just send us a short mail with your questions, and then we will attend, because there are a few questions on evaporators and forced circulation versus natural circulation and things like that. Yeah, so we would love to answer all that. You please send us a mail with your coordinates, and then we will definitely get back to you. Yeah, I think as a concluding slide, this is what I would like to talk about. What you saw today was a very, very high helicopter view of all options available, in terms of treating effluents. But the first step is always the basics. When we are able to segregate understand the effluents, segregate them, and then manage the design of the plant, that is the easiest to implement. The minute, the same is true of our municipal networks also. If we're able to segregate rainwater properly, then away from sewage water, then we are actually solving two problems. The sewage system works then, very, very well without any plant upsets. At the same time, the rainwater also is conserved and taken to groundwater recharge. Yeah, minute we are having a combined sewer network, we are not able to run the STPs efficiently, and we also waste a lot of rainwater. So this is very basic. We're talking about pipelines, segregated tanks, so that we are able to look at each effluent independent of the other one, and then figure out the best way to handle it. If at all, if mixing up makes sense, we will do that. Yeah, but we should have the choice of being able to handle them separately. And again, for effluent recycling, the experience and detailed knowledge of the effluent and prior experience is a very key factor, because ETP, when when the plant is designed and planned, everybody has got a rough idea of the ETP, but no one knows for sure that this will be the effluent, this will be the pattern. It always comes out much later, because we assume certain raw water qualities, and if this raw water quality changes, again the discharge from the basic freshwater plant itself affects the ETP loads a lot. Yeah, so suddenly in Chennai we see between summer and rainy days, the groundwater parameters change by 20-30%. Yeah, so, and this obviously will have an impact on the ETP of any facility. Yeah, so that experience and effluent stream knowledge is critical. Yeah, and technologies are always there, and new ones are coming up all the time, and all of these have got a a very can have a very high impact on how we handle our waste streams. But it is no alternative for to avoid the basics. The basics are effluent, understanding the effluent and making sure that they are well segregated and characterized. So I would like to end the session with a simple statement: water is everybody's business, and together we can make a difference. Yeah. So this is has to be a slogan for each one of us. We have an impact on the consumption and on discharge, and as long as we act responsibly, the whole society and the whole nation can also see the difference. And I would like to thank the organizers of IWMA for giving us this opportunity. We hope that you found the session also useful and informative. Thanks to all the participants. We have had almost 150 participants. At some point in time, it's reached to 107 now. Thanks a lot for your attention and for your interest in the topic. And we wish you all the very best. Please stay safe during the COVID days. All the norms regarding social distancing, I think, becomes even more important with the new reports about the airborne nature of the virus. So please stay safe. Please, observe all the distancing norms. And we wish you all the best. Thanks a lot.